The F-15 has pulled 9 Gs since 1976. The F-35B, a generation newer, far more advanced, is officially limited to 7. And the reason isn't what you'd expect. It starts with a helmet that weighs 5.1 pounds on the ground, but exerts over 45 pounds of force on a pilot's neck at 9 Gs. The engineering trade-off buried inside that number is one most discussions about this aircraft never reach. Official numbers tell a story that does not quite add up. The F-15, fielded in 1976, has held a published 9G sustained rating for nearly 5 decades. The F-35 arrives with a new generation of avionics, sensors, and cockpit integration, yet its G limits do not form a simple upward trend. The F-35A is rated for 9G, matching the Eagle's legacy. The F-35B, designed for short takeoff and vertical landing, is capped at 7G. The F-35C, built for carrier operations, sits in the middle at 7.5G. The published limits in official flight manuals are as follows: F-15 9G, F-35A 9G, F-35B 7G, F-35C 7.5G. These are not marketing slides, they are operational numbers enforced by flight control laws and structural monitoring. So why does a 5th-generation fighter, despite decades of engineering advances, post limits that do not clearly surpass its predecessor? If you have followed this channel's investigations before, you know what to do. The rest of this channel is built the same way: direct evidence, no shortcuts, and a willingness to question the official story. The numbers alone invite a closer look. The answers, as we will see, run deeper than airframe stress or engine thrust. They live in the cockpit, where engineering trade-offs and human limits collide. Design philosophies set the course for everything that follows. The F-15, conceived in the early 1970s, was built around a single purpose: to outmaneuver any adversary in the air. Its cockpit was stripped of excess, focused on visibility and pilot endurance. The helmet, lightweight and no frills, was designed to minimize neck strain during the hardest turns the airframe could sustain. Every ounce mattered because every ounce multiplied under G-load. By the mid-1990s, a new vision took hold. The Joint Strike Fighter program imagined the cockpit as a digital command center. The F-35 would fuse sensor feeds, night vision, and targeting data directly onto the pilot's visor. The helmet became a nerve center, integrating 6 cameras, microdisplays, and active noise reduction. This leap in capability came with a price. The Gen 3 helmet's mass climbed to over 5 pounds, nearly 50% heavier than its predecessor. The center of gravity shifted forward, and the pilot's neck became the structural link between technology and survival. These diverging priorities, raw maneuverability versus integrated awareness, set up a trade-off that would echo through every engineering decision. The next step is to see how these choices translate into the physics of the cockpit. In that space, the numbers become forces, and forces become limits. A helmet's true burden is not measured on the scale. It is revealed when the G forces hit. The F-15H GU-55P helmet at 3.5 pounds and the F-35 Generation 3 helmet at 5.1 pounds might seem like a small difference on the ground. In flight, that gap becomes a gulf. At 9G, the F-15 helmet multiplies out to 31.5 pounds of effective load on the pilot's neck. The F-35 helmet, under the same acceleration, weighs in at 45.9 pounds, an increase of nearly 50%. The numbers are simple, but their consequences are anything but. The physics are unforgiving. Torque on the neck is the product of effective weight and the distance from the joint to the helmet's center of gravity. The F-35 helmet, with its integrated optics and power module, pushes its center of gravity forward by about 2 centimeters compared to the legacy design. That means the moment arm is longer and every extra ounce is leveraged further out. The result is about a 90% increase in neck torque for the F-35 helmet at 9G, compared to the F-15 helmet. This is not just math on paper. Pilot cohort studies have tracked a corresponding rise in neck pain and strain, especially during sustained high G maneuvers. There is a popular claim that neck injury risk scales with the cube of helmet mass. The math for that comes out to a 3.1 times higher risk when jumping from 3.5 to 5.1 pounds. But dig into the biomechanics literature and the picture is more nuanced. Peer-reviewed studies show that muscle activation rises linearly with helmet mass, and pain increases with the square of torque, mass times distance squared. The cubic relationship, often repeated on forums and in safety briefs, actually comes from impact modeling, not sustained G-loads. In the cockpit, the risk grows fast, but not quite as explosively as the cubic myth suggests. The upshot is every extra pound, every millimeter of forward balance multiplies the biomechanical challenge. For the F-35 pilot, the helmet's engineering promise comes with a measurable cost. The next step is to see how these numbers play out in the test seat, where theory collides with the realities of ejection and survivability. In 2015, the Martin Baker US-16E ejection seat underwent a series of critical tests. Engineers, joined by Air Force officials, used full-scale F-35 cockpits and anthropomorphic dummies rigged with sensors to measure neck forces and acceleration. The results were immediate and troubling. For pilots weighing less than 136 pounds, the combination of the Gen 3 helmet, weighing 5.1 pounds, and the violent ejection sequence produced neck injury metrics that far exceeded survivability standards. During high-speed ejections up to Mach 0.92, the head snapped forward with more force than the airbag system could safely absorb. Helmet wind blast pressure peaked at 55 kilopascals, a level that lighter pilots could not safely withstand. The main concern centered on the neck injury criterion, abbreviated NIC, which combines peak neck moment and angular acceleration. In these tests, NIC values for lightweight pilots wearing the Gen 3 helmet nearly doubled the safe limit. The helmet's forward-shifted center of gravity, already a challenge in flight, now amplified the risk during ejection. The seat's airbags, meant to cushion the head, instead contributed to a pitching moment that pushed the neck beyond its engineered tolerance. The response was swift. In October 2015, the Air Force issued a safety bulletin. No F-35 pilot under 136 pounds would be cleared for solo flight until the risk could be addressed. This restriction was formalized in a military flight release, grounding a segment of the pilot corps while Martin Baker and program engineers searched for solutions. The US-16E seat, proven on other aircraft, now faced a unique challenge from the F-35's integrated helmet and cockpit system. Martin Baker's team responded by testing a lighter helmet and revising the airbag deployment sequence, reducing inflation pressure and adjusting timing. By mid-2016, injury metrics for lighter pilots dropped back within acceptable bounds. Further testing through 2021 confirmed that with these modifications, pilots as light as 103 pounds could eject safely. In May 2024, the Air Force lifted the weight restriction, validating the US-16E seat for the full operational range. The episode remains a rare instance where test data directly shaped policy, exposing the hard limits set by physics and enforced by regulation. Structural choices and cockpit integration have immediate consequences for pilots. The F-35B's 7G ceiling is not just a paper limit. It is enforced by the demands of its vertical lift fan, which cannot handle the fatigue cycles of higher G turns. Software in all F-35 variants deliberately slows the G onset rate, easing pilots into turns to reduce neck strain from the heavier Generation 3 helmet-mounted display. Pilots report that even at these lower limits, the helmet's forward center of gravity and mass amplify neck fatigue, especially during high G maneuvers. These design constraints are not abstract. They are felt in every sortie, shaping how pilots fly and how far they can push the aircraft. Engineering teams are already chasing lighter, less punishing solutions. The upcoming Generation 4 helmet aims to shed nearly 2 pounds compared to the F-35's current system, targeting a weight closer to the F-15's legacy gear. Early prototypes swap out bulky optics for micro-LiDAR and slimmed-down displays, shrinking both mass and forward center of gravity. Meanwhile, the next-generation air dominance program is testing concepts that sidestep the helmet burden entirely, exploring wide-field cockpit displays and remote sensor fusion. The F-22, which never adopted a full helmet-mounted display, continues to pull 9G with a traditional heads-up display and a lighter helmet. Even the Chinese J-20 is rumored to use a sub-4-pound helmet, suggesting the trade-off is universal. Whether these advances can restore high G performance without sacrificing awareness remains an open question, and that could reshape the next generation of fighter design. Ejection at speeds above Mach 0.8 remains a grey zone. Deceleration forces can spike past 20G in milliseconds, yet pilot and helmet survivability in this regime remains unproven. Should we accept a cockpit where the wind blast envelope is more theory than fact? If you value this kind of scrutiny, subscribing tells the algorithm to bring the next investigation your way, and a like signals there is an audience for depth over hype. The question stands: in a real high-speed ejection, would the system hold, or would physics write the final verdict? Today, a 5.1-pound helmet and a 7G ceiling remind us that engineering progress isn't linear. When human limits and ejection physics dictate the edge, air power's future relies on tough choices, not just new tech. The truth is, operational reality still outpaces marketing. You know what to do.